All right, let's jump right into this explainer. Today, we're decoding the invisible, underlying rules that govern absolutely every single movement in our universe. If you're tackling Class 11 physics, specifically Chapter 5, well, you have officially arrived at the absolute cornerstone of classical mechanics. And we aren't just going to sit here memorizing dry formulas, right? We're going to visually dissect exactly how, and more importantly, why, objects move the way they do. So here's our roadmap for today. First, we'll hit forces and the inertia principle. Second, Newton's 3 laws explained. Third, momentum, conservation, and impulse. Fourth, friction, the opposing force. And we'll wrap it all up with dynamics in the real world. Now, before we get bogged down in the math, I want you to think about this for a second. Why does an elevator ride make you feel momentarily heavier right when it starts going up, but then gives you that crazy stomach drop feeling when it goes down? I mean, your actual mass hasn't changed at all, right? Keep that specific feeling in the back of your mind, because by the end of this explainer, you're going to see the exact decoded mechanics of why your perceived weight shifts like that. Okay, let's get into Section 1, forces and the inertia principle. Forces basically fall into 2 distinct camps. On one side, you've got contact forces. These literally require physical touch. Think about the tension in a rope you're pulling, the normal force from the ground pushing back up at your shoes, or the friction fighting you when you slide a heavy box. On the flip side, we have action at a distance forces. These act kind of like magic across completely empty space, operating entirely through fields. So gravity pulling an apple from a tree, or magnetic forces snapping 2 poles together without them ever actually touching. But here's the thing. When these forces actually try to act on a body, they are met with resistance. And that resistance is called inertia. Inertia is really just a measure of an object's mass. It's basically nature's ultimate stubbornness. It's resistance to change. And we see 3 types of it every day. Inertia of rest is exactly why you fall backward when a bus suddenly accelerates. Your body just wants to stay still. Inertia of motion is why you jerk violently forward when that same bus slams on the brakes. And inertia of direction, well, that's why raindrops fall in a straight line and literally cannot dodge you on their own, which is exactly why you have to hold an umbrella directly over your head. Moving right along to Section 2, Newton's 3 laws explained. Let's break these down quickly. Newton's first law is simply the law of inertia we just talked about. An object at rest stays at rest, and an object in motion stays in uniform motion unless some external force messes with it. The second law is where the actual math kicks in. Force equals mass times acceleration, which is the rate of change of momentum. Think about it like this. A strong adult can easily shove a heavily loaded shopping cart and get it moving fast. But a baby pushing that exact same massive cart, basically zero acceleration. Same massive object, totally different force applied. And finally, the third law. For every action, there is an equal and opposite reaction. And looking at how bodies interact here perfectly captures that third law. When 2 bodies interact, the forces acting between them are exactly equal and completely opposite at the interface. They act on different bodies entirely, which is why they don't just magically cancel each other out to zero. Like, imagine block A resting right on top of block B. When a force pulls block B forward, friction acts between them. The friction force on block A actually acts to pull it forward, while the exact same magnitude of friction acts on block B to resist its motion. It's a perfect, totally equal balance at the interface. All right, Section 3, momentum, conservation, and impulse. So, what actually happens when we add velocity into the mix? That brings us to linear momentum. It's defined super simply as mass multiplied by velocity. It basically represents a body's sheer quantity of motion. If a lightweight bicycle and a massive delivery truck are rolling down a hill at the exact same speed, the heavier truck naturally carries immensely more momentum. It's just way harder to stop because it requires far more force to change its state. Now here is the absolute golden rule of momentum. In an isolated system, total momentum is fiercely conserved. It stays completely constant. Let's look at the classic gun recoil example. Before you pull the trigger, the gun and the bullet are just sitting there at rest, right? Total momentum is 0. When fired, the bullet shoots forward with positive momentum. To keep the total system momentum locked at 0, the heavy gun has to shoot backward with an equal amount of negative momentum. Now, because the gun has way more mass, its backward recoil speed is much smaller than the bullet's forward speed. But the overall momentum, it balances out perfectly. But wait, what if that momentum changes literally in the blink of an eye? That, my friends, is impulse. Impulse is the average force multiplied by the time duration of the impact. It's incredibly brief and it is incredibly powerful. Think of a bat violently striking a baseball.
the force spikes massively over just a tiny millisecond. And honestly, this is exactly why we package fragile stuff in soft foam or straw. The soft packaging essentially stretches out the time duration of an impact. By prolonging that time, the peak force drops dramatically, which completely saves your fragile items from shattering into a million pieces.
On to Section 4, Friction, the opposing force. You can kind of think of friction like a stubbornly stuck door. When you first push a heavy box, it doesn't budge right away. That is static friction perfectly matching your push. It climbs and climbs until it hits its absolute peak, which we call limiting friction. That's the tallest bar on our chart here. But the second you push past that specific threshold, the box slips, and friction drops right down into the kinetic friction zone. Notice how it's suddenly easier to keep the box moving than it was to start it? And sitting all the way at the bottom, rolling friction. That incredibly low resistance is exactly why humanity invented the wheel. Friction isn't always the bad guy, though. Sometimes it literally saves our lives. But on a sharp, curved road, friction alone isn't always enough to keep a fast-moving car from sliding outward off the pavement. That is exactly where the banking of circular roads comes in. By actually tilting the road inward, a component of the car's normal force, the ground pushing back up, gets directed horizontally toward the center of the curve. This assists the friction, creating the necessary centripetal force you need to navigate that turn safely without spinning out. Let's bring it all home with Section 5, Dynamics in the Real World. Okay, remember our elevator question from the very beginning? Let's finally solve it. When a lift is totally stationary, or moving at a perfectly steady, constant speed, acceleration is essentially zero. The reactionary force, R, which is the floor pushing up on your feet, matches gravity precisely. Here, R equals mg, so a weighing machine would read your actual weight, and you feel completely 100% normal. But hit that up button and boom, the lift accelerates upward. Now, according to F equals ma, the floor isn't just supporting your weight anymore. It's actively pushing harder into your feet to accelerate your mass upwards. The reaction force becomes R equals mg plus ma, so your apparent weight literally increases. Mathematically and physically, you are pressing down harder on the scale. You genuinely feel heavier. On the flip side, going down, the lift accelerates downward and the floor literally drops away from you a bit. The normal reaction force required to support you completely decreases. Now, R equals mg minus a. This sudden decrease in the upward push on your feet is exactly why you get that crazy, weightless, stomach-dropping sensation. Now, if we zoom out from lifts to connected bodies, observe how a single external force, F, pushes on a whole system of 3 connected blocks, M1, M2, and M3. Because they're in direct contact, they have to move as one single unit. The force distributes straight through the interfaces, creating those internal contact forces we talked about, but it results in a shared, common acceleration for the entire system. You can calculate this super easily by just dividing the total pushing force by the total combined mass. And it's the exact same logic for pulley problems, just swapping in tension. To solve these, you just methodically step through an analytical process, like a recipe. Step 1. Isolate each mass and identify the forces, like gravity pulling down and tension pulling up the string. Step 2. Apply Newton's second law, F equals ma, to each mass completely independently. Step 3. Formulate your system of equations. And step 4. Just solve them simultaneously to find the internal string tension and the system's common acceleration. And throwing an inclined plane into the mix? Well, that creates this awesome tug of war. A rough inclined plane allows a block to slide down using only a specific component of gravity, meaning way less force is required than if you were just dragging it flat. But depending entirely on the angle of the tilt, it introduces an opposing kinetic friction force that scales directly with the normal force. It's this perfect mathematical balancing act of gravity pulling down the slope and friction fighting tooth and nail to hold it back. So as we wrap up this explainer, the big takeaway is incredibly clear. Whether it's understanding the inertia that violently jerks you forward on a stopping bus, calculating the exact tension in a complex elevator cable, or plotting the necessary friction on a banked highway curve, Newton's laws are the undisputed rulebook of the universe. They take the absolute chaos of motion and they turn it into perfectly predictable, solvable mathematics. Which leaves us with this final thought. If these incredible laws seamlessly govern absolutely everything, from the subtle ripple of coffee in your cup when you walk, all the way to the massive orbits of distant galaxies, what invisible forces are shaping your trajectory right now? Keep observing the physical world around you, because physics is happening everywhere, every single second. Thanks so much for joining me on this explainer, and keep exploring.